Let's review what we discussed yesterday. So what I'm trying to do is to review the concept of multi-resolution, the ability of representing the signal in a multi-resolution sense. Yeah. Over here, the signal is very, very far away. The tiny low pass. Over here, the signal is very, very fine. And as you see all the detail and structure of the signal. After this, we'll review the two-scale relation equation that deal with the scaling function in wavelet, and then we'll show how to solve those equations. Okay? So after that, we have a break, and then we have I will spend about an hour and a half on application of wavelet. And then after the break, from 11:50 to 12, I have some research topic that I'm working on. I can discuss some of the topics. That's the plan. Okay, so we present an example yesterday regarding how to take a piecewise constant signal. Right? We have this particular signal right here, something like that. 1/8 unit signal, and then we see that we can take this signal and we can decompose it into a fourth approximation by taking averages of every two coefficients, right? And then we have a detailed signal. We add them together, we have the original signal. The interesting construction is from a 1/8 piecewise constant signal. The post approximation will be 1/4, 1/2, and 1. Okay? And through this construction, we notice that the basis function of V0 is phi of t, and the basis function for W0 is W of t. And this is basically we're dealing with piecewise signal. So this is a straight line, 1, that will be phi of t. And then to capture the change, we capture it in W of t, which is 1 and minus 1. Okay? And you can see that if you combine these two together, you can construct a space where basis function will be phi of 2t. And the detailed space will be the basis function W of 2t. And you can iterate on this process to W of 4t, W of 4t, and phi of 8t. Right? Now, if I use this kind of process, we said that I can write x of t in terms of basis function only in V3. As I can say that x of t can be written in terms of summation. Okay, I can say a phi of 8t minus k, and this is ak, right? I'm going to say a 3k, okay? So you see this is V3. Right? So basically, phi of 8t is the basic function, and any signal in that piecewise constant to 1/8 interval will be a linear combination of this. K can go is a positive signal. It will from 0 to infinity, and K from 0 to 7. Your support is from 0 to 1, and so on. Okay, so that's how, using the basis function phi of 8t, I can represent any signal x of t with a 1/8 unit interval. Okay, that's using only space V3, right? This is only using 3. But I know that another way to do this is to represent using V2, W2. So the second line I'm going to write is using V2, W2. Okay? So the first summation, okay, we'll deal with phi of 4t minus k. That is the V2 space. Okay? The next one will be a summation of W of 4t minus k. This is the W2 space. Right? So I will call this A2k. A is listed before approximation. Okay? And this is to be B2k. Right? And in our example, what are the coefficients for B2k? Remember it's -1, -1, 0, 0. Right? That's in our example yesterday. Okay? And this is using B2 and W2. Well, how many other ways can I represent the same signal? 2 more ways, right? I can have V1, W1, and W2. Okay? So basically, we'll keep this the same. And we have V1 and W1 here. We have 3 summations where this one stays same. The V2 space stays same, right? So in V1 space, I have summation K, A1K, phi of 2t minus k. That's the V1 space. Okay, and I have W1, which is summation K, V1K, W2t minus k, and then we'll just have this copy over. We have summation K, V2K, W4t. Okay. So this is V1, W1, and W2. Because V1, W1 will give me V2. Okay? And the next one is very, very simple, right? You can see that. And then V0, W0, V1, W2. So we decompose this into 2. Right? We have summation in K, A0K, 3 of t minus k, that's V0. And then you have W0 with summation in K, V0K, with t minus k. Then I have the other 2. This is the one that we use V0, W0, V1, W1, W2. Right? So in general, you always have a coarse approximation space, right? You always have a V, the low pass representation at that one particular space. And then depending on what you want, where are you at the resolution, you have various details. Okay, so the most general way of writing this is, so the most general. What do you have? You have a space, right? You have summation in K, A0K, 3 of t minus k. And then you have a combination of this, okay? So I'm going to have a double summation now, right? Let's go. The first one is J in K. J will go from 0, 1, and 2. Right? Now if I have, 1/16 is quite constant, then J from 1 from 0 to 3, and so on. Right? So this J is telling you, what are where are the detailed signal. Right? For this case, it's going from 0 to 2 because our signal, x of t, is 1/8, right? 1 is 1 and 2 thirds. So 0, 1, 2. Okay? And then K, E, J, K, W, 2 to the J, T minus K. Right, so see, we have 1, 1T, 2T, 4T, and so on. Okay? So that's another way to, review. We didn't do it yesterday, but this is another way to actually see how to decompose a signal, right, into different resolutions. Any questions there? Now, if we compare P of t, which is the basis function in V0, and phi of 2t, which is the basis function in V1. We know that I can combine, right, this to get that. Or I may combine this to get that. So I know that V0 is in V1. So I can write phi of t, this linear combination of phi of 2t. It's not K, 2. But the weighting factor that we use to represent is actually 2 H naught of K. In this example, what is H naught of K? There are 2 here. So it's 1/2, right? If I take this and I shift it by a half, add together, I get this one. So there are 2 terms in here, right? The term where K is 0 and 1, and the quantity is 1 and 1. So it's 1/2 and 1/2. In this example here, H naught have value of 1/2, 1/2. You recognize that this is hard, right? Hard is 1/2, 1/2. So again, hard is a basis function that is bitwise constant signal. Okay, so hard you'll be able to represent bitwise constant signal. Okay. Furthermore, I also notice that W0 of t, W of t, also in V1, right? Because W of t look like this. Right, that's W of t. So I can combine this with a shift and flip. Okay? So in general, right, I have W of t, which is a smaller space, right? With 2 summation H1 of k, phi of 2t, k. So both are called the dilation equation. Right? For dilation equation. And in this example, in the hard example, what is H1? 1/2 minus 1/2, right? Because if I take t and I shift it by 1/2 and flip the value, so I have 1/2 minus 1/2, and that will give me W of t. Okay. Now this. So this particular quantity here is only for hard. But in general, right? In general, if you construct it like this, you have various form phi of t. Okay? So what I'm going to do next is we're going to take this dilation equation and we ask the question: given H0 and H1, how do I find the corresponding basis function for those spaces? Okay? So there are several ways of doing this. I will show you 2 ways. One is the brute force. It's hard to do, but let's do it anyway to see what's going on. And one is a much faster way to do this. Okay? So So the next topic is taking the dilation equation and discussing way of how to find phi of t and w of t given the coefficient x0 and x1. And yet we recognize that here also that x0 is the low pass filter associated with the filter bank construction, right? Because in this step, as an h0 down by 2, h1 down by 2. Okay? So that's what we're going to do next. To take this equation and discussing way to solve it. Okay, this is in the book. This is called Cascade Algorithm. I'm going to discuss one of them, and you can generalize it to the other one. Okay, let's stay with the first equation. What it will say is that I can do the following. I'll have an iterative process. I can start with the initial form for phi, and I can iterate it. Okay? So at the I plus 1 iteration, it will be built on the I iteration. So it will be 2 summation in k, it's not of k, I 2t minus k. If it's converged, right? You know, if I go to infinity, it will converge to a closed expression or a curve that you can plot, right? And let's take the case. So we have several different examples, okay? And we choose phi naught of t. The initial condition for phi will be a box from 0 to 1. Now the book has several exercises. As long as for all the choice of phi naught of t, as long as you have unit area, you can prove that it's always converged to the same solution. But you're not going to have to prove that, okay? But the book has some exercises. If you look at the section on this topic, you actually have a problem that shows that. Okay, but the first easiest one to do is using a box from 0 to 1 with 1 to 1. So that's kind of area, unit area 1. Okay, so let's take several examples. Take the case, the hard case. Okay, where the filter is 1/2, 1/2. So what I'm going to do next is, we're going to take this example, which we know the solution already. Right? That's the solution. Okay? Take this, let's go through the process, look what's going on. Take this example and plug it into here and see what happens. So it implies that the I plus 1 iteration will be 1/2 times 2 is 1. Okay, so I have phi of 2t at the I iteration plus phi of 2t minus 1. Right? In this case, the proof we can have phi 1 is phi 0 of 2t plus phi 0 of 2t minus 1. Right? So let's plot them. Phi 0 of 2t is that. Okay? That's phi 0 of 2t. And what is phi 0 of 2t minus 1? It's the same, shifted by 1/2. Right? Because 2t minus 1 shifted by 1/2. So that will be your phi naught 2t minus 1. So in one iteration you converge. So this is the ideal case, right? The easiest example where no iteration. What you start out with will be your solution. Okay? All right. Take another example. 2/3, 1/3. If you notice, right, it's both still low pass filters. Okay? 1/2 is average, so low pass filter. 2/3, 1/3 is still a low pass filter. Not a very good one, but still low pass. Okay? So let's see what happens here. Ci equals 1, T equal to 2/3, so I'll give you 4/3, Ci 2T plus 2/3 Ci of 2T minus 1. Is that clear? I'm doing okay. So let's start with this. What is Phi1 equal to? Phi0 2T, which is this, string in, right? And scale by 4/3. So you have 4/3 to 1/2, right? And then you have 2/3, okay? 1. This is Phi1. T. What's the next step? The next step, Phi2 T, second iteration, is based on the first iteration, based on this solution. Right? So I'm going to take this one here, I'll shrink it in, and scale by 4/3. Right? And then shift, scale by 2/3. Okay? So using this solution for the second iteration, we have, let's see, 1, 2, 3, 4, right? 1, which is Phi second of T. Second iteration. What do I get? 69, right? So it's 4/3 square. Okay? So it will be 4/3 square. So 69. What's the next one? 49. 89, right? Because 4/3 times this. So it's 89. Okay, so that this is this. 4/3, 3 of 1, 2, 3. And then 2/3, 3, 1 of 2, 3 minus 1 would be this, shift, by scale in, shift, and then scale by 2/3. So tell me what is it? 49? 89? Right? Okay? So tell me, if I go to infinity, what kind of curve do you have? What is the limit for this go to infinity? Is it stable? Is it bounded? Who thinks it's bounded? Who thinks it's not bounded? It's not bounded. Why it's not bounded? Because if this is 4/3 square, what is 2? What is this value? What is it? 3? 4/3 cube, right? 4/3 bigger than 1. Is it that goes to infinity? So this is the case where there's no solution, no bounded solution, right? Okay, you have infinity. Okay, so this is the case where there's no solution. So there's some kind of a extra condition on the filter H0 such that we have a solution. So can you compare these two choices? Both are low pass filters, right? Why is one converge and one does not converge? So I'm just putting a cross here. It's not convergent, right? No solution. So what is the difference between these two choices? Such that one you have a solution and one you will not have a solution. transform of this one. If I plot, pole 0 plot, where's the 0 for this one? At pi, right? At minus 1, because you have 1/2 and 1 to the inverse. So when 0 equal to minus 1, you have a 0. There's 1 0 here. Is there a 0 at pi here? No. You see that there's no 0 on the frequency, right? On the unit circle. So that's what you need. This is called condition approximating P, or AP in the book. For approximation with degree P. The number of 0 at pi dictate your approximation. If you have 1 0 at pi, you can approximate piecewise constant signal. If you have 2 0 at pi, you can approximate piecewise linear signal. If you have 3 0 at pi, you can have quadratic. 4 will be, third power, so forth. So you can. We're not going to prove it. Okay, it's in chapter 7 of the book. But here's what you should remember. What you should remember is the correlation between the 0 at pi to the approximation. Let me make a short table here. P, okay, and the approximation. If P is 1, you can approximate piecewise constant. If P is 2, you can have piecewise linear. So you can have T. If P is 3, you can approximate a constant, constant 1, a constant, piecewise linear, and piecewise quadratic, and so on. Okay, you have 4, you can approximate any function. You can represent it by 1, t squared, t cubed. If you recall the first few lectures, we have example where this is 4 0 pi, and so on and so forth, right? And those are the ones that people use. If we want to have, a decomposition, a useful one. Useful in the sense that you be able to capture, represent exactly, right? Piecewise constant, piecewise linear, quadratic, cubic, and so on and so forth. So it's a proof in the book saying that if you have, P0 pi, you can actually represent piecewise or up to t to the p minus 1 order function. Okay? So that's what you should remember. If you're interested in the proof, you can look at proof in the book. Okay? And if you have questions, email me. Next example. One quarter, 1/2, 1/4. So this is my coefficient x naught of k. So far we discussed 2 types, right? Solution. Now we have 3 types. So instead of having 2 terms, how many terms do I have? 3 terms. So let's write it like that. Okay, so I have 3 of I plus 1, t, 1/2, right? 1/4 times 2 is 1/2. 3i, 2t, and 1, 3i, 2t minus 1, 1/2, t, of I, 2t minus 2. Any questions here? Basically, substituting the coefficient that's given to the direction equation. Again, we'll do the same process of starting with this box and see whether this has a solution or not. Okay? So let's see. It's V1. What does V1 look like? This string in, scale by half, right? We have half to 1/2, and then 1 to 1, and then 1/2 to 3/2. The first thing we realize that if the coefficient is symmetric, your function will also be symmetric. You can prove that. Okay? I'm not going to prove it. You can prove that if this is symmetric, that's symmetric. Okay? Then this is also symmetric. Right? This is not symmetric, you don't have a symmetric solution. This is symmetric, you have symmetric. That's one way to check, right? In this process, you might make a mistake. Okay? Quick way to check is that if your solution is symmetric, then you might be on the right track. If it's not symmetric, you're wrong. Okay? So the second one, phi second C. What does it look like? Take this, we straight in. So this is from 0 to 3/2, from 0 to 3/4. Okay, so you have 1/4, 1/2, 1/4. So 1/4, 1/2, 1/4. This is 3/4. 1/2, that's 1/4. Right? This is C1, 1/2, C1 of 2C. How do I plot C1 of 2T minus 1? Do I start here? No, when do I start? 1/2. And what value is 1/2? Exactly this guy, right? There's no scaling. Right? Exactly 1 times that. So we take this, string in, we shift by 1/2. Okay, so we start at 1/2, we value 1/2, go up to 1, down to 1/2. This is 1. Okay? And where's the other one? It's symmetric, right? So we have exactly this guy. But where's it go to? To 1. It's going to be this. So if they add them together, right, the sum. So the red color will be the final solution when you add them together, right? So you have 1/4, 1/2, 3/4, 1, 3/4, 1/2, 1/4. It's a staircase with quarter, right? Any questions here? So, P2, quarter, quarter. Tell me how to draw P3 of C. What should it look like? We start at what value here? 1/8, right? We like this, okay? And so on. And then it will be, going down this way. What is this value again? What's the ending? It's 1/8, right? It's 1/8. What is this guy? So here is 7/4. Two here. What's that distance? 1/2, 1/4. Okay, that's correlation to 1/2, 1/4. It's 1/2 to the whatever iteration is. Right? So this is 2. What's that distance? 1/2, 1/4, 1/8. So this is 60. What's the limit? If it is infinity, what does phi of t look like? Where this goes to? Go to 0. Where that limit goes to? 2. And where the center of symmetry? 1. The half. Okay? Now, that's a solution. So let's look at where the 0. So where are the 0 for this filter? If I plot the whole 0 plot, where are the 0 for that choice of filter? Pi. How many 0 pi? 2 0 pi. How do I see that? Well, if I factor out 1/4, what do I get? 1/4, 1 plus 2 the inverse plus beta minus 2. Right? That is 1 plus the inverse square. Then I choose 0 pi. Choose 0 pi. You have a piecewise linear. The basic function with piecewise linear. You can combine piecewise linear to that piecewise function, right? Okay? Okay. And I'm going to still use this as the starting point, okay? This is the case for half. Let's look at half now. We have P of t, 2 h0, 3 of 2t, 2h1, 3 of 2t minus 1. Right? I have 2 coefficients. So let's group this one as m 0, 3 of 2t, m1, 2 of 2t minus 1. In case of car, m0 and m1 is 1. And this is true for arbitrary system with 2 types, 2 coefficients. Okay? So I'm going to do the following. I'll say, what is C naught equal to? Now, here is the time index, okay? This is t. So this is t. Look at this equation and tell me what is phi naught equal to. Plug phi of 0 to here. What do I get? M naught, phi naught, right? And 0, phi of 0. Do we have this? Phi of minus 1. What is phi of minus 1? 0. So you only 1 part. Okay? What does phi of 1/2 look like? What I'm trying to do here is I'm trying to find solution for 0, 1/2, 1/4, and so on. If you have all that, you can actually plot the curve, right? And that's how the computer is finding those points. Okay? What is phi of 1/2 equal to? M0 phi of 1. Phi of 1 is 0. Right? It's only from 0 to 1. Yeah. That doesn't include 1. Because it already includes 0. Okay? We have only this term. M1 of phi of 0. Let's do one more row and see what's going on. Phi of 1. What does phi of 1/4 equal to? 1/4 M0 phi of 1/2. And if I plug this one in here, what do I get? M0 M1 phi of 0. Okay? Or 3 of 3/4. 3/4 it'll be 3/2, that's 0. It'll be M1. Phi of 3/4, that's 3/2, that's 1/2. Right? It'll be 1/2, which is M1 and 1 phi of 0. So let's see what's going on here. Let me discuss a bit here, right? So I start with count 0. This is 1. I look at 1/2. And 1/2 all depends on count 0. And I look at 1/4. 3/4. What depends on 0 and 1/2? I mean, it depends on 1/2, but then you can convert it back to depend on 0. Okay? Now let's do one more and see what's going on. Let's do phi of 3/8. Now, then what's the next step? The next step is getting 1/8, right? 3/8, 5/8, 7/8. And so on and so forth. Okay? So that's how you do it. That's basically how you compute this in computer, right? You start at 1 point, you find 1/2, and then you have 1/4, and you have an 8 and 16, and so on and so forth. Depends on how many, what is the resolution? You're going to start at 1/8, that's what you have. But that's what you plot anyway, right? You plot this quick point on the computer. You don't plot 116 and 3/8, right? We plot all this quick point. Okay, so that's the process. The process goes from 0 to 1/2 to 1/4 to an 8 and so on. So the next thing I want to do is going 1/8, 3/8, 5/8, and 7/8, which is too much. Let's look at only 3/8 for now. What is 3/8 equal to? It will be M0 phi of 3/4, right? The M0 phi of 3/4, which is what? It's right there, right? M0, M1, M1 phi of 0. Okay, tell me how to find phi of 7/8. Without knowing anything. Who can see the pattern? Phi of 7/15, 16, sorry. Equal to Okay, so you guys see it, right? What is 3/8 in binary? Binary.
2 power 1, 2 power 3.
Tell me the binary point.
1,
0, 1, 1. Right? This is 0.5. Okay? So that's 0, 1, 1 is 3/8. That's 1/2. That's a quarter, that's an 8. 3/8 is a quarter plus an 8. That's 3/8. 0, 1, 1. Okay? What is 7/8 in binary?
1, 1,
1, 1, 1. So, and 1 and 1 and 1. What is 7/16 in binary? 0, 1, 1, 1. So M0 and 1 and 1 and 1. Okay? You can prove that's a part that you want to do. Okay? As long as you can write it this way. And it's easy to do it if you have two-tap system. Okay? So for two-tap system, I know how to generate this on computer. It's very easy, right? I mean, programming computers is trivial. Okay? You know M0, you know M1. That's all you have to know. You start out with field 0 is 1. That's your initial condition. Okay? And you go stage by stage. The first resolution is 1/2 resolution. Right? Next one is 1/4, 1/8, and so on and so forth. Doesn't matter, how far you want to go to. You want to go to 10, 2 to the 10. You know exactly how to compute this. Got to it. So the only thing you have to do last is, if I have a longer length filter, right? Let's say length, 5 or 6. I need to somehow write it in this form. When I can do this, I'm done. Okay? Actually, this is the order 5. 5 is, this is 1, right? So that's a stopping point. Okay? So this means that I have 0, 1, 2, 3, 4, 5. That's what I meant by adding with 5. Remember the first step that we have here is we identify the integer point, the initial point, right? And here, what do we have? This is 0 to 5. Those is your first resolution. It's on integer point, right? And then if you, so that's the first step. And then the next iteration in yellow, in here. Let's call it blue, okay? 1/2 blue. It's actually 1/2, 3/2, and so on. Okay? So that's what we have. So let's look at the equation, right? V of t is 2 summation h of k 3 of 2t minus k. So here is, you have 1 point only. So that's a scalar point. If here you have 5 points, you have a vector. Okay, so you have t of 0, 1, 2, 3, 4. I'm writing the first equation here. Right? In this case, this only has one integer point. Right? That's a scalar equation. Right? Here, how many integer points do I have? 5. So I have a vector equation now, right? Vector equation. So now instead of a 1 by 1 vector, right? I have a 5 by 1 vector. And those are my integer points. Next one will be my half integer point. When I can do that, and everything else is just going through this. It's a matrix multiplication. Is that clear? Okay. So I have 2, right? 0, 1, 2, 3. So our job is to find that matrix. Matrix, choose on that matrix to be n0. So who can tell me how to find that matrix? What does it depend on? Depends on that equation. Right? In this case, k goes from 0 to 4. Okay? So, what is phi of 0? If you plug in 0 in here, what do I have? Phi of 0 is 2 summation k, h of k, phi of minus k. By phi is 0. So, tell me how many terms do I have here? One term. What is k equal to 0? Right? So, where's that term? Here? So x of 0. I'll phi of 1. 1 minus k. How many terms do I have? 2 terms. 2 terms? Is it 1? 2. So how many terms do I have? 3 terms, right? So k equal to 0 is okay. K equal to 1 and 2 is okay. So what is this guy? 2, right? 2, 1, 0. Because x of 0 times phi of 2. X of 0 times phi of 2. And so on. Phi of 2 with 4 minus k. So we have a whole range, right? So we have 4, 3, 2, 1, 0. Of phi of 3. 3 is 6. Do you have k equal to 0? No. Do you have k of 1? No. So k of 2, right? So where do I start? Here? 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 H of? That's phi 1, right?
Under H2, H4, H4, yes.
5. Actually, sorry. Let's go to 5. 5, 4, 3, 2. Okay? And then this will be 5, 4. So you see that, you see how to start with matrix. What is that? Even polyphase. What is it? Odd polyphase. Even polyphase. Odd and so on. So you know exactly how to construct this matrix, right? The first column is the even polyphase. Then you shift by 1, they go in pair. Okay, so you know exactly how to construct, how to build that matrix once you see it. Okay? The next one is we want to do phi of 1/2. When that's done, we're done. Okay, I'm going to save time and give you the solution. Okay? So this is phi of 1/2. 3/2, 5/2, 7/2, and 9. 5 by 5 matrix. This will be phi of 0, 1, 2, 3. Okay? And you can show that there's a factor of 2 here. This is it's 1, it's 3, 5, 0, 2, 4, 1, 3, 5, 0, 4, 1, 3. And so because this panel is really hot. Okay? And again, you know, find that matrix M1. Again, the first, so basically, that is right here, M1 right there. Right? Okay? So, you know, when you see it, the book has a general expression for it, but you can program it very, very easily. So what we're doing here is we are writing the correspondence for, right? Okay, so you have phi naught, here is a scalar, that is a vector. You write phi of 1/2, here's a scalar, that's a vector. So you have m naught, which is 2 times that matrix. You have m1, which is 2 times this matrix. Are we done? You know, for a quarter, I know exactly what to do, right? So on and so forth. I can multiply this matrix. Are there anything missing on this? So how do I start here? How do I start in this case? I know this is 1, right? So that's work out, okay? We have phi. Let's go to phi of 0. Okay? Because this vector phi of 0 is m0, right? m0 phi of 0. Let's call this the same m, okay? That's a matrix, that's a vector. Then how do I find phi naught? Given m0, how do I find phi naught? Louder.
M0 minus I non-zero.
Okay. So tell me the name. Don't tell me how to do it. What's the name say? What is phi of 0? It's an eigen vector for m naught. And the eigenvector? Which one? M naught is 5 by 5. They have 5 eigenvalues, right? Which one? Which eigenvalues? 1. This saying that M naught must have eigenvalue to 1 of them. I don't care what the other one is. If it doesn't have eigenvalue to 1, you cannot have any solution. And that's the case for R. Right? If you look at R, R is the case when you have eigenvalue to 1. It's a simple one, right? This is 1, so 1 equal to 1 times 1. But arbitrarily, okay, if you put on 4/3, 2/3, and 4, 4/3 in here, it will not have eigenvalue to 1. The third converge. And you can actually show that with eigenvalue to 1, meaning that you have 1 0 pi on the filter H naught. They all related. Okay? Okay? So the sufficient condition for all this to start is that you have to have an eigenvalue 1 for m naught. Okay? And then, if this is the case, then you can start, right? And phi naught is the eigenvector associated with its eigenvalue. When you can do that, then you can start everything, because this is dependent on phi naught. So this is m1 times phi naught. Okay? So this is a very strong condition on the filters. And you can show that this condition is the same as the filter H naught of Z has 1, 0, and pi. It's a theorem in the book. I showed it. Okay? So let me have a discrete point. How many points do I want to compute? Right? If you have, I want a very fine resolution and so on and so forth. I might want, 2 to the 5th or 2 to the 10th. Right? Iteration. I have very fine representation of my basis function. But if I don't care, if I only want 2 to the 3rd, I can stop at at the 8th iteration. Right? So this particular process here using recursion is a way for us to very efficiently implement or compute the basis function. Right? Because how many points that you need, you can basically compute, right? And the algorithm here is that if you look at 7, 8, if we see the binary representation is 1, 1, 1. It's basically m1, m1, and m1 of phi naught. Okay? So that's easy, right? For the case of hard, you can find this easily. So if I want to use the same process here for a longer length system, right? In this case, all is fine. I have to somehow, write a correspondence form. Okay? As in phi naught times m naught, phi naught, t1 half, and so on and so forth, right? And the way to do this is using a vector matrix representation. And you can show that given H, I can always find this matrix M naught, M1. And if this is the case, I can basically use the binary representation, right, to compute any point. Provided that I know where to start, right? So what is the condition so that I can start this process? The condition is that phi naught has to exist, right? And looking at this equation here, phi naught is an eigenvector with eigenvariable 1. And you can show that this is the same as having the filter having 1, 0 pi. Okay. So we find the condition on the matrix M naught and or the filter H naught such that there's solution for those discrete points. But the solution might not be smooth, right? I can start, but it might be, that. Okay? There's no guarantee that this gives you a smooth solution. It could be like this. Okay? Compare this particular solution with this one. What's the difference? What's the difference between a smooth solution and this solution? Frequency or derivative, right? Things like this. You might not have any derivative for those points. And this you can find derivative. Okay? So what I'm going to do next is I want to see what additional condition on H naught such that the derivative exists. Right? So what if I take the derivative of phi with respect to t? and see what's the corresponding equation, and I do the same thing, and hopefully I can find a corresponding condition on either M or H, such that this derivative exists. I can go for phi of 2 and so on. Okay? The more derivative exists at this point, the smoother the basis function. Right? Let's look at the first derivative and see whether you can make any deduction toward the condition on M naught or H naught. Okay? So I need to help. What is the derivative of phi with respect to t? 4 phi of t prime the whole thing here is 2 become 4. Exactly the same form. So if I were to do exactly the same thing using phi primes instead of phi on this. So I have phi prime of 0, phi prime of 1, phi prime of 2, and so on and so forth. Would this change? This will be phi prime, right? Would this change? No. What changed? This 2, right? Become 4. So what would be the vector phi prime of 0? I'm looking for something like this. Okay? What would it be? 2 M0. So what is the condition on M0 now? So that the derivative exists at those points. 1/2 eigenvalue, right? This means that if I put 2 over here, I have a 1/2. Look, it looks like a eigenvector equation, right? So you have M0 and phi prime 0 is 1/2. So it means that M0 as an eigenvector is equal to 1/2. And you can show that it's not 2, 0, half. Forcing one eigenvalue equal to 1 is much easier than forcing 1 and 1/2. Right? It's a much more constrained problem. And in fact, you can show that if you start with something eigenvalue equal to 1, if you add one more 0 at time, go from 1 to 2, then you have lambda equal to 1/2. You can actually show that. It's one of the exercises in the book. Okay? Is that clear? So you can start with filters that might not have derivative. Exist. What you do is you put an additional 0 there. And you can show that the corresponding operation in the matrix set side is that eigenvalue of 1/2. What if the 4 prime? 8, right? Summation is not of k. Phi prime double prime 2t minus k. So obviously you can generalize this. So phi double prime of 0 will be 4 and 0 phi double prime of 0. So if you want second derivative equal to 0, I mean not equal to 0. Second derivative exists. So even smoother. Then your M naught have to have eigenvalue equal to 1/4. Right? So you have 1, 1/2, 1/4. So the more derivative exists, the more eigenvalue structurally that you want. Right? 1, 1/2, 1/4, 1/8, and so on and so forth. That's the limit, okay? 5 by 5, right? You cannot have 1, 1/2, 1/4, 1/4, 1/8, 1/16, and so on and so forth, right? You can have 5 eigenvalues. So this means that I can have 1 up to 1, 1/2, 1/4, 1, 1/2, 1/4, 1/8, 1/16. Only 5 and the value of this matrix. Minus 5 by 5. And that's the smoothest choice you can make. And that's the case when you have 1 plus Z inverse to the 5th power. The next 40, so tomorrow until Saturday, Professor Draft will discuss in details of the basic building blocks in compression. I'm giving you an overview of what's going on. Okay? So here's the website, my own group website. So if you want to see what I'm working on, you can actually go to the website here and take a look at it. And so after this part, I have another talk for about half an hour on topics that I'm doing research right now. So you see that I have about 10 different projects. I may be choosing 3 or 4 and discussing about those projects somewhat in detail. And then so you can see a flavor of what I'm working on. And all those projects and demonstration videos, so on and so forth, presentation, papers will be on the website. Okay? A few words about UCSD. So who have heard of UCSD before? Let me try to motivate why do we need compressions. And then there are 2 choices of transforms. So far we discussed wavelets, right? And you can see that wavelet is a way to represent. It's a representation. So wavelet in the compression engine is appear as a processing block, right? It's a transformation block. So we compare wavelet to DCT. DCT is also discrete cosine transform. It's also another way to represent signal. So we compare what are the trade-offs between different transformations for similar codecs. And then we'll talk about this in JPEG and MPEG, which is DCT based, and then we'll talk about wavelet transform. And then at the end of the talk, I have a demonstration. Okay, using 5 wave, which we use today. And you see it on the image, what's going on. Okay? So compression. So what this slide is trying to say is that over here you have your source, okay? This is the video source. And the source can be a combination of several different screens, right? And if you want to send this source losslessly, you need a very, very big pipe, right? A very high density pipe. And then you can get very, very good quality. Or with no compression, you can have a smaller pipe, but then you can only display or compress a part of the image. So if you want to compress everything, compress and display the whole video scene, then you need somehow to take this video or this image, go to a compression engine, we call it C for compression, to eventually reduce by factor of 64, for example, right? From very big size to very small size. Send it over to a narrow bandwidth, and then on the other side we decompress, right? To get the image back. Now, so there must be some way of designing C and D together, right? C and D have to work together to get a good compression. So in this talk, I'll discuss how to compress. So compression is a way to represent data spatially and also temporally. Okay, so frame coming in and so on. Here, so the next few slides, I'll discuss several examples of compression. So for example, for Disney have a Disney cruise, right, in the ocean. And suppose Disney have a celebration in Disney World or Disneyland. So if they want to broadcast this live event over to the cruise, which is far away, they need to do compression, right? So they have to compress, and then have to send it to the satellite, and then the satellite will beam down to the ship. Okay, so that's one example of using compression. In war, okay, you have fighting, right? So you need to be able to communicate, right? If this is the Pentagon, you will recognize it, 5 right? The Pentagon. So the Pentagon will will receive data from the, from the finding area, right? All the sensor transmit over here back to the Pentagon, and then the Pentagon will discuss, will tell all this what to do, and so on, right? So all this data is not only data but also images. What's going on? And you have to do it in real time. In gambling, go back, right? This is one of the biggest, market driving technology. Is that in the betting, right? It is one of the huge area when you're to be able to let the people here to bet on multiple races, right? They want to come in here and not only betting on one, but maybe 10. Okay? So you want to be able to see what's going on in all this betting. That means that you have to be able to compress and code all the video stream back to here and then show it, right? So that's one application of using compression. So in all this application, what is the most expensive component in this system? The channel. Okay? The compression engine, the box that we built is cheap. Well, it cost you $1 million. $1 million is not cheap. It's right? But over time it's very cheap. Because renting, this is they charge you, right? Megabit per dollars. So the compression box that you buy is a one-time cost. It's a fixed cost. The cost, the heavier cost, is in this everyday use, right? You use it every day. The box can last you for several years. But the more bit that you send, the more cost you have to accumulate. So this is much more costly compared to the compression engine that you built. Right? So if you can reduce the bandwidth by 10%, you can recover the cost very, very easily. Right? Is that trivial? Yes. Okay. So this is why we have MPEG 1, and then MPEG 2, MPEG 4, and now 264. Every time you have a new standard, it's much more complicated. But every standard comes with the fact that you can reduce the bandwidth by a factor of 2, for example. To compare MPEG 4 with 264, that's a 50% reduction in compression. Even though it's much more complicated, you don't really care, right? You have a very fast machine right now, a lot of memory, doesn't matter. What matters is the bandwidth. Right? Bandwidth is the most expensive thing. Okay? Bandwidth, you have the spectrum, right? And you chop it up, and and you sell it, right? And those bandwidth spectrum are very, very expensive. The most expensive thing in the whole world, right? So that's why you need compression. Good compression. Is that clear? Yes. Okay. So let's just take a few examples, right, of compression. So what I'm doing here is I'm just listing the obvious way to compress. Well, easiest way is to remove extra blank page in the chapter, right? So when you scan in a book, you don't have to send a blank page. Or you can do PKZip or WinZip, whatever, right? That's one way to compress. But those are lossless compression. Right? This compression is lossless in the sense that you can reconstruct bit by bit exactly. And for many applications, you want to have lossless compression. Okay? Now, in the lossy compression, who have heard of reader dynamics? Okay. Who have heard of truyện ngắn? You have a truyện kiều, right? It's a big volume, they're huge. And they have a shorter, thin version of truyện kiều, right? So those are the idea of compression is that you don't have to read the whole big thick chapter books. You can read a simplified, a simple version of that, and you can still know what's going on. Right? So that's one way of looking at compression, is to be able to read a condensed copy of particular, very, very complicated books. That's compression. or DVD. I'm sure you have looked at. You see VCD, DVD. That's use effect 1 and effect 2. That's compression. And you have, you have MP3 music and so on and so forth, right? That's another way of compression. So there's a lossless and lossy compression. Okay? And the idea of lossy compression is compression such that you still capture most of the information, right? In DVD, it looks pretty good, right? Okay? As long as you cannot see the artifact, the error, it's okay. If you have a very fast scenery, if we watch Kung Fu movie, okay, when they actually doing this, right, flying up and find it, if you freeze the frame, what do you see? A lot of artifact, right? It's blurry, doesn't look very good. But if you play it as a video, you don't see the artifact. So video allows you to actually do more compression, right? If you freeze the frame, you see the error. But if you play it, the whole video sequence, you don't see the error at all. So your eye is acting as a low pass temporal. Okay? Filters. Okay? So that's this would be the compression. So this is just saying that, at quantum VGA SIP side, the size is always very large. And NTSC is very, very large, it can be even larger, and so on and so forth. That's when you need compression. So let me go to the how video is structured. Okay? Okay. So what I'm showing here is a video sequence. A video sequence is a collection of pictures, right? How many frames per second? 30 frames per second for normal progressive video. 24 frames per second for film, and so on and so forth. Okay? So depending on what is the format that you are seeing, you will see that there's a number of pictures coming in, and how many. So let's say 30 frames per second. Okay? There's a structure, so the hidden structure is a group picture. GOP is group of picture. And the idea of having group of picture is the ability for you to search randomly. Right? So you can search in the video by having the structure. You can go into just by group of picture, you can actually access to any of the starting point. Okay? It's much harder to access the one in the middle. Because the one in the middle is actually related to anything in between. Okay? So the group of pictures allow you to have random access search within a video stream. Okay. And for every picture, that's a picture, we divide it into slides. Each of the slides has size 16 by multiple of 16. So a slide could be one block of size 16 by 16, or it could be, half of that whole slide, right? It could be the whole thing. Okay? And this is basically for error concealment. If an error appears at one block, it will propagate within the slides. So basically, you can, reconstruct within the slides. Okay, so slide is for error correcting code, error concealment technique. And each of the blocks within the slides, okay, decompose into, it will be a 8 by 8 block. And each of the 8 by 8 block will be a luminance and a chrominance. The chrominance is subsampled by 2 because the bandwidth is lower compared to the luminance. Okay, so all you have to remember here is picture, is video consisting of group of picture. In each group of picture, you have several pictures. Each picture consists of slides. Each slide are blocks. Each block you have luminance, which is the intensity black and white grayscale level. And and you have the color component. Okay. So within a compression algorithm, you have several ways of coding. Okay? We have the I type. I stands for intra-coded picture. The P type is for predictive coded picture, and B is for bi-directional predictive coding. So let me take an example, right? Suppose he is videotaping me, right? That's a videotape right there. And I'm standing right here. It captures 30 frames per second. If you compare one frame to the next frame, what are the changes? Is the background change at all? No. Is my lower bottom change at all? No. My hand, right? Okay? So if you be able to predict temporally, so this is temporally, right? Temporal means time, over time. Okay? So the idea is that for every picture, if you code with respect to the other one, right? So coding my picture, respect to this one, respect to the next one. You see that there's very little change. Only change is in the hand and the mouth and the eyes. Okay? So those are called predictive coding. So in this particular example here, you have 12 frames. Okay? 12 frames is the number of frames. Each of the frame here, the first one is coded independently. That's called intra-coded. This frame is coded either using DCT or wavelet. Okay? Does not do any prediction at all in a temporal domain. It can predict spatially, but not temporally. The idea of having an iframe is that if you want to search and reconstruct, it just displays iframe. Okay, when you pause, it will display iframe and so on. And then you predict the P frame. P frame is having 4, right? 1, 2, 3, 4, and so on. Having 3, sorry. Right. Okay? So this P frame is predicted by the I frame. Okay? And so the P frame predicted by the I frame. And then the B frame is predicted by I and P. It's both way prediction. Okay? So the coding, the display order, this is the number of frames. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. At 12, picture is a row picture. So you have I starting at frame 1, I starting at frame 30, so the 12 frames. In the row picture. Okay? So all of these frames within the row picture, they're coding together. And then you go to the next one. Right? Next row picture. Within this, the way that you code it, it goes 1, and then 2, and then 5, and then 8. Because those are the P frames that you have to code first. When you do that, then you have to go back. Right? And you code 1 and 2, and then 3 and 4. The code is better than 1 and 2. And I have 2, go to 5, right? After 4, go to 5, and it goes 6 and 7. Because 6 and 7 depend on 2 and 5. After 7, you go to 8, which is the P frame. So 8, 9, and 10 depend on 5 and 8, and so on. Okay? Now, if you look at this, what's the trade-off between group of picture and the complexity? Suppose you want suppose you have a very small memory in your machine. Do you have a huge big group picture here? Or very small group picture? Smaller, right? Because there are some delays in here. Okay? And a small group picture is not very efficient in coding. It's not enough in terms of prediction. Okay, if you have a very big group of picture, it's much more efficient in coding because you can predict better, more efficiently. But that's a trade-off between delay, between the complexity, and how well it does. So typically in a typical codec, you have group picture control. It's about 1/3 of a second. So this slide shows motion estimation, how to predict. Right? So here is the way to do that. You take a current frame. Here's a current frame. We divide current frame into a block of size 60 by 60. Here's an example of a 4 by 4 block. Each of them of size 60 by 60. For every block in the current frame, for example, block of 60, you want to search within the previous frame where is the best match. Is that clear? For example, if I'm doing this, right, going this way, what is the best match? It's a shift, right? It's over here. Okay? So for every block, when I'm doing over this, like this, the best match is the one that appeared before me, right? So that's the idea. The idea is that you will search. That's your current block. You will search within the window size for the best match. Now, what does best mean? You can compare error, right? If you look at the mean square error, or maximum error, and so forth. So there are many ways of doing, what is the best match? Okay? And the window size, the search size. The bigger the search size, the more accurate you're going to get. Right? But it's more complicated because you have to do it pixel by pixel. Okay? That's the full search. There are all the fast algorithms that Professor Graf will discuss in terms of searching. Okay? Like diamond search, hexagonal search, and so forth. But the idea here is that every block, you find the best search, the best block, and then you only have to send a motion vector. So that's very efficient. Instead of sending a pixel, 16 by 16 is 256 pixels. Instead of sending 256 numbers, you're sending only 2 numbers. You're sending the vector, which is a 2-dimensional vector, right? Only 2 numbers. So compare 256 with 2. What is the compression ratio? 2, 128. Right? So if you can predict perfectly, you can achieve 128 to 1 compression. There's no way you can do perfectly, right? So there's some error. Okay? So in compression, you have motion vector and you have some error. The better you can predict, or the friendly the motion is. Look at this. This motion is basically translational motion, right? This shift. If your motion is basically shift, you can predict very, very well. You can predict well in a very, very little compression. So in this example here, the best match for this block 1 is the same block over there. So motion vector is 0, 0. Okay? The best match for 2 is this one. The motion vector will be down and to the left, and so on. Right? So if I send a motion vector, I already know this frame, right? It's the previous frame. I know how to find this frame. Okay? The motion estimation. So here's an example. Here are the motion vectors from 2 different frames. So I'm going to compare the error. This is the error after you send this motion vector. And here is just a different subtraction. And one way to code is just to subtract. Right? The difference. No motion estimation. If you still subtract, here is the entropy. There's a lot of structures in here, right? And here I'm inverting it. So dark meaning high energy. Okay? So there's a lot of high energy structure all around. Compare this with this. Which one has more energy? That has more energy, right? But this needs more bit to code. So if you do motion estimation and compensation, you require less bit to code the error. So here is the very generic codec. Okay? The frame coming in, group of picture. You see that there's a path here. This path is for intra-frame coding. That's coding the first frame in a group of picture, consisting of DCT, of quantization, and entropy coding. Okay? And then everything else will be predictive coding. And how do you predict the coding? Predictive coding is motion estimation. Right? And the motion estimation will give a motion composite frame. When you subtract it, you have an error frame, and the error frame, which is the frame, which is this frame right here. Okay? An error frame goes through the same process. But now you have different table for error frame. So you do motion estimation in here, and this motion estimation is the search, and so you have to be able to reconstruct, right? This I-frame. So that's the I-frame. That's the previous frame. You have to compare the previous frame with that current frame. So there's a process of intra-frame. That's a process of predictive here. So let's look at several applications that you can actually use it at home. Okay? Well, Sony, about 2 years ago, they tried to design a unit here that you can take in, in the satellite cable or whatever the format coming to this box. And this box would work as a TiVo box, Uno TiVo. Okay, TiVo is basically a recording device. So you want to watch a movie, but you cannot World Cup soccer, right? If you miss a particular match, you can record it. So this box has a coding process in there that you can code, and then later on you can play playback. So when you go home at night, you can switch on the TV, switch on the box, and then replay that world match, soccer game. Okay, so there's a coding and compression and decompression. And you can also save it for storage, right? You can give this movie or this particular match to your friends, right? Either using DVD or memory stick. In particular, the stick you can actually play back either by wireless link to a PDA. So you don't have to be right at in front of TV to watch it. You can watch a scaled out, not on a high definition TV, but on a scaled out copies on your phone or wireless devices. Okay. Now this wireless link, you can replace this by an IP. Then you can watch it anywhere in the world, right? So now, what's this company called? Slingbox. In the US, they sell a box that connected to your PC. So in your phone, there's a compression engine in there, right? Because they're not going to send this video uncompressed. It's very, very expensive. Okay, so they have to send it compressed to a tower, right? And the other way around is if you subscribe to a service, you can watch live events, right? This example here, there's a professional camera here. There's a compression engine in here. It will, video and live event. This is the race, right? The race, okay? And if you subscribe to that service, you can see that race in real time, for example. And security, this is the big market in the US. After 9/11, a lot think about security. So now you have multiple cameras. If you install 100 cameras throughout your whole structure, if you don't compress, there's no way you can bring 100 camera, 100 video stream high resolution onto your system, right? So you have to compress. Okay, so there's a lot of compression engine and search capability, and we can add in there another capability to view on a PDA, for example. before, if you don't have this, you have to be at the station to see what's going on. And that's not very efficient. Okay, so before, right, if you don't have this capability, the policeman or the security guard has to be at the station on that roof to see it. If you see something is wrong, he walk over there and things change. He doesn't know what's going on, right? But if you have this ability, you can actually see it on this PDA while working there. You can actually track what's going on. Okay? So that's another application for video. Alright. So the next thing I'm going to do is I'm going to discuss, so we have applications while we do compression, right? So now I'm going to discuss about image compression. Professor Draft will discuss about video compression. Okay? So now it's basically intra-frame coding right now. Okay, I'm going to talk about wavelet versus DCT and all the advantages of using wavelet platform. So this slide shows DCT-based algorithm. So you have a LiDAR image here. We take image, we block of an 8x8 block, apply DCT. That's how DCT coefficient looks like. And then you can do reconstruction. In terms of filter bank, you can show that this DCT is the same as an 8-channel filter bank. So there's a blocking process here. That's block 8x8 block, right? So that's going to scan into a block. You can apply 8x8 block transform, and you can do processing and inverse transform, so on and so forth. And what I'm showing here is a basis function associated with those 8 bands. So image compression, this is a better way to represent. Okay, you have a transform, a quantization, and decoding. And here's the DCT coefficient. Each of this is an 8x8 block. Okay, let me try to explain it. On DCT, right? Who have seen the DCT before? DCT, you have DC value, you have high frequency, right? So each of this block, you see the top left, upper left corner, that's the DC value. And you see the AC coefficient. That's one block, that's the next block, and so on. So if you give countable blocks, right? It's like 1, 2, 3, 4, 5, 6, 7, 8, and so on. Those are the blocks. Look at this area. This is very bright, very low, high intensity, low variation. What do you expect to see in the DCT coefficient in this area? 1. You see one large value, everything else is very, very small, right? Because basically it's a constant intensity block. Okay? So we look at this block right here. That's a block associated with this area. What do I see? I see that there's a 1 coefficient there and very dark around it. Okay? So that's how you see, how to read. An area where you have a lot of structure, texture information, and you see that it's not only 1 pixel, that's over here. You have many, many different pixels. So you have not only DC value, but you have several different AC value, and so on. So the idea is to apply transformation, quantization, and decoding, and the inverse operation. In terms of JPEG coding, right? DCT, quantization matrix, the way we code for DC and AC is different. Okay? AC is highly correlated. If you look at this example, if I basically read this coefficient, the upper left coefficient, the DC coefficient, from one block to the next block, they're almost similar, right? Because the variation from here to here are very much constant. They should have very similar DC values. Right? DC measure the average intensity. So you don't want to code them independently. You're going to code in differential coding. So they used to be DPCM, differential coding. There's different, take different into different successive sample. Okay? So in DC, we use Huffman table with the differential coding from sample to sample. AC is zigzag scan, and the Huffman table for that. Okay? The coding is the reverse process. So here's an example. I'm looking at the area around the eyes of man. Look at the bottom of the picture. What do you see? Constant intensity area, right? And look at the distribution of DCD coefficient. One large value and thing very, very small. One large value and very small. And this DC value are almost the same. Because the average intensity here are almost the same intensity. Right? When it becomes darker, this value is smaller. Look at areas around here. Look at this block. This is very, very dark block. So what's that DC value equal to? Very, very small. Right there, you see. Okay? And so on. So if you look at this, you actually see there's not much happening here. There's something happening over there, right? Because there's a large value, there's some leakage, and so on. Okay? In compression, what you do is you truncate this value, right? And reconstruct. I'm not sure whether you see it, but the iris look very good, right? You see blocking artifact? I'm not sure in the back, you might not see it. People in the front, can you see? They have block here, yes. Right? So those blocking artifacts come from a quantization. In this example, okay, I computed out. The size 64 by 64 is 8 bit. So that's about 32 kilobits for that particular block. After I compress, is average is about 20 to 1 compression. And in this case, you have blocking artifact. And that's to be expected. Why? Because JPEG, the way that they design JPEG, is only for 4 to 1, 6 to 1, 8 to 1. In your phone, okay? Who has phone that can have image? Most of you have shown image, right? If you take a picture, do you know how much compression they have there? It's about 4 to 1 compression. And they will not give you 8 to 1 or 16 to 1 because they want to give you a picture that looks good. And JPEG is designed to have 4 to 1, which is very, very good. 8 to 1 is pushing it. Okay? Here you have 20 to 1, we expect to see error. Okay? So the limit of JPEG is about 4, 6 to 1 compression. So here is compression on Barbara, which is a big image. We see this image before, right? Original, and this is compressed at about 15 to 1. Now, far away, it looks pretty good. But I see some artifact there, over there, and so on. Okay, it's hard to see. And also, big image easier to compress than small image in general. Okay? This is 25 to 1 and 40 to 1. Looks pretty bad. Okay, so again, this is reinforcing the fact that JPEG is designed for 8 to 1 or so. You shouldn't use it to 20 or 40. Alright. Wavelet transform. So the way this way appears in the other direction. Okay? So the idea here is that we use a filter bank iterated this way. We shoot it. So we have a low pass approximation and detail. Okay? And in this example, I'm choosing the 97 tab global shift, which give me a very smooth basis function to construct. Okay, so this is the decomposition, that's the construction. So that's the difference between, so wavelet is a global transform. It works on the whole image. DCT is a local transform. It's worked only on block A by A block. Which one is better? Who think DCT is better for compression compared to wavelet? Again, DCT only look at a local structure, A by A. No correlation between structure. The correlation is in the coding. Okay? Wavelet look at everything together. Of course, the more information you have, the better you should be able to use it. Right? So if you look at the whole image, you'll be able to do a better job. Okay? That's why wavelet win over DCT. What's the trade-off? The trade-off is this one requires much more energy. You have to load in the whole image to do this. Okay? So that's the trade-off. So here is the same eyes, okay, blender, and that's how it looks like. It's kind of hard to see, but that's a DC value. It's pretty bright, okay. And here are different subbands. So you can see that's one, another one, a third one. So let's review how it works. That's a one level. Okay, so you have, low pass, low pass, low pass, high pass, low pass, and high pass, high pass. And you see that this one captures the horizontal information, right? That's captured the vertical, this is diagonal. And the way to do that is, there's one level to the wavelet transform. Apply one more, taking this block. Okay, and you see that they're correlated. You see that if this is large, it's also large, right? And they are corresponding structure here. Okay, you can see the structure. And this is 3 levels, and so on. So that's how wavelet works. So what I've done is I take the ladder, okay, the whole ladder. You can see ladder, okay, kind of hard. So this is actually the hat here, the face there, right? Okay? It's too bright. And can you see ladder here? Yes. You see the eyes here? The feather? Okay? Can you see ladder here? Yes. See the eyes? The mouth, okay? See ladder here? Yes. So what I'm doing here is I'm taking this guy, must scaled up. I brought that 16, you can see. The typical is very, very, very dark. Very small, but it's there. The idea of wavelet coding is that you're trying to find correlation across scale. Okay? If you go this direction, that's the same direction, right? A different resolution. Go this direction, that's diagonal. The same direction, but different resolution. And over here, the same way. So the idea of wavelet coding is that if there's a 0 value here, very small value here, it is very likely that over here also very small, and so on. Because they're correlated. Okay? So it's the idea of 0-3 coding. What it does is it scans this guy. This half resolution one. It's searching for a very, very small value. It's at a threshold. Right? Okay? If coefficient below that threshold, it's assigned 0. And it will search for the corresponding location here. This is 1 pixel. This is 2 by 2. This is 4 by 4. We will form a tree called 0, 3. Right? So the idea here is the pixel 0, they will assign a corresponding group 0 and so on. And that is a gain encoding. And it turns out that there's a lot of small values here. I'm scaling this up by 16 so I can see it, but this is very, very small. And that is again, so you are taking advantage of the correlation across scale. So that's what I'm saying, right? Actually, though it's got a code. Okay? The artifact of JPEG is in your blocking artifact, right? The artifact of wavelet is a bringing artifact. Because you have multi-resolution. So the basic function will be long when you have high resolution. So if we look at Yogi here, right? This looks like I'm throwing Yogi and then I dip it into water. It's like smearing, okay? Like the ink smear, smear, right? So you can see that at edges, which is high frequency, right? This edge is in frequency. It's basically a very large change, right? So it's a high frequency. In compression, we truncate or we assign 0 to high frequency. Those are the one that capture detail. Okay? So the area we make this equation are in area of texture and high frequency. The area that we have, axis like this, you will see artifact. The area with axis like this, you see artifact. But you see the ring artifact? Yes. So it's interesting that JPEG 2000. In the year 2001 came out, right? And people evaluated it. And they see this kind of artifact. This is 32 to 1 compression. Okay, so compared to JPEG, you win a factor of 4. Okay, from 8 to 32 now. But you have this artifact, and people get used to looking at blocking artifact. But they accept blocking artifact. They don't like the cleaning artifact. They say it's not good. Okay? So depending on what we're used to also. Certain kind of artifact might not be good. If you're used to looking at blocking artifact, this might not look good at all. Okay? Okay, so my next thing I want to do is I want to show you in real time how the comparison between JPEG and wavelet. Okay? So using the same file wave, the toolbox that you have seen yesterday, let's look at 2D. I want to load in Barbara. Okay? That's the image that we have seen before. It's very speaking, it's very hard to compress. Okay. Now, if you want to take notes, okay, the way to use compression is Control O. Okay? Control O brings up this screen right here. It allows you to have JPEG on this side or wavelet on this side. So what I'm going to do next is I'm going to show you to compress it using JPEG and then compress for the same liquid using wavelet and then compare the performance. Okay? So in JPEG compression, you can choose a quality factor. The higher the quality, the better it looks. The higher liquid. So I'm going to choose very low quality now. Okay? I'm going to choose 1. So, and you can, for other kind of compression, you can use it here. But this stay with JPEG for now. Apply. I want to save. Let's say this in JPEG. Okay, we save on JPEG, and let's say Barbara JPEG, right? And let's load. Okay, so that is the compression with quality factor 1. Now, does it look okay? Yes? No? It's kind of small, hard to see. Let's zoom in, see what happens. I'm going to display this at large scale. That's the original image. Now you can see, it's pretty bad, right? You see the blocking artifact. Okay? It's trying to represent it using only one or two coefficients. But it's not enough coefficient to represent the details. So basically just a constant density graph. Let's zoom in one area. Which area should I zoom in? So if you want to zoom an area, you go there, and you right click, okay? Zoom. Wow. There's no way you know who it is. You know the face. You know there's a nose, right? There's maybe a mouth, maybe an eye. Maybe. So right? Okay, so it's not good, right? So what do we do next?